Yeah, so you're welcome to today's class. Can you all hear me?
Yes, sir.
Yeah, okay. So we want to begin with the class. I'm going to share my screen whilst your other colleagues are joining in. And we're going to listen to a very exciting lecture, okay, which is going to combine both the theory and some practicals using MATLAB, okay, which was, I think, my last lecture before we came online during the main school last semester. Okay, it's the video is also available on YouTube. You can watch it hereafter, or I can still send you the links and you can view it on YouTube. Okay, so let's begin. We still have a number who are yet to join, but I'm sure once Gabriel has posted a link, then everybody should be in by now. Okay. So we have a very exciting article here, okay, which I wrote in 2015. It's a simulation for, first of all, to determine the dynamics investigate the dynamics, okay, of malaria infection, okay, and its consequence on the lifespan of people in malaria infested countries, a typical case in Ghana. So data was taken from the Ministry of Health, okay, to populate the model, the statistical model, which I was using for the prediction. And then based on that, to run simulations to determine what will happen when rates go down as against the use of mosquito nets and the use of anti-malaria drugs. What will going to happen to the lifespan of people within the country? Okay, so it was a very exciting paper. I'm sure you are reading whilst I'm speaking to it. Okay, because I'm talking to it to at least to give room to those who are not yet in to come. So the paper is basically talking about transmission of Plasmodium falciparum, okay, which is one of the 4 malaria causing species, okay, which causes very severe forms of the disease, okay, and sometimes the effect is irrevocable. And due to that, there are a number of states, okay, we've looked at all this already. There are a number of space we can have a state where you are susceptible, means you are likely to be infected. You are not infected, but you are likely to be infected. That's one state. Then there is another state where you are infected, okay, and there is a last stage where you were infected and you did not recover, okay, you did not go back to the susceptible state, you rather ended up dying from malaria, okay. And statistics have shown that malaria is the highest killing disease in Ghana and in most of these African countries, okay. So people can die from malaria, people can be infected, but will remain in the states, okay. And then people can be infected and then recover from the disease by the application of what? Drugs. Okay, so this fantastic paper which I wrote also predicts the lifespans of human being, okay, which was found to be 55 years, okay, confirmed by differential model and simulation by WHO, okay. I used a Markov modeling technique, okay, to predict the lifespan of human beings in Ghana, and WHO used a differential model to also predict the lifespan. At the end of the day, we all had the same lifespans, okay, which further validates, okay, the model that was used in the prediction of lifespan and also in the behavior of malaria transmission. And if you remember, this is a very famous paper. The first time I presented the findings from my simulation and modeling was in Ghana Biomedical Convention, which was in 2012, okay, which led to a national policy in 2013. If you recall, we were supposed to use anti-malaria drugs, okay, every 12 days to prevent malaria, okay. That finding is in this work of mine, okay. I presented it first to indicate that the first time to non-severe malaria is 11 days, and the only way to prevent that 11 and some few hours, 11 days and some few hours. So to prevent that, you have to make use of anti-malaria drugs, okay, before the 12th day to prevent malaria. So it's a very famous, popular paper which attracted the attention of so many people. I'm going to play it. I think we have a lot of people in class now. So I'm going to play the video, listen attentively, and then we see the connection between the video and then what we are learning in class. Once you go down, you realize, let's look at the key things of this. It says Markov model was then extended to estimate what the best transition probabilities for an individual to become infected and also to recover. Okay, and when you go down, it says what the outcome of simulation by decreasing the probability of infection and increasing probability of recovery by 5, 10% respectively respectively, right, of their corresponding prevailing probabilities at 1% interval shows the gain of what life expectancy of this in 2 years respectively. The expected time to infection in average duration of non-severe malaria was found to be 11 and 17 days respectively. Life expectancy from start of experiment is what? 55 years, which gives the average lifespan of 59 years for a living person, okay, in Africa. I hope the sound is clear enough for you. Gabriel.
Sir, please, it's
not
echoing a bit.
Not really, sir.
Okay, then I'm going to share the sound from the computer. Okay. Now, when you check this, we'll be doing this in a couple of lectures away, looking at Markov Chain model. When you come down, you'll be seeing this today. That's the Poisson distribution. Okay, the Poisson distribution, you see that, and then the cumulative frequency distribution of the Poisson process are based on exponential waiting times. We'll look at this also shortly. Okay, so it is this equation or these models, these statistical models we're coming to look at. That is what basically was used in modeling.
Sir, please, it's not really clear.
And running all the simulations you are seeing there. Okay, the sound is still not clear.
Yes, sir, it's
Yes, sir,
some
the
sort
other
of
one was better.
interference.
The other one was better.
Yes, from my side, please.
Yes, sir, the other one was better. With this, the background is not clear.
Okay. Okay, so let's do it once and for all. I think I'll speak to it. So what this basically is trying to demonstrate, okay, is that we can see the cumulative distribution model as these are the simulation results, okay, for the stabilization of the process, okay, and then when you come here, we are also looking at the stabilization, the probability distribution for first transition of the process, okay. So we have two graphs here, okay, two graphs here which tell us how the process stabilizes, okay, and once the process has stabilized, we can make estimations. So we can see that the sampling time was 10, okay, over 10 days. That gave us 11 days of stabilization, time to first infection, and then the time to first recovery, okay, from the disease. Okay, so this paper gives us a highlight of what can be achieved. So these are the final values. This is the life expectancy, okay, from the disease, time to, okay, infection, and time to what? Recovery were also shown. Now, key things from this article, which we just looked at, are the facts that probability distributions, okay, are very, so in studying the behavior of random variable, it is far better that after we do the estimation, we also run some graphs, okay, some graphical representations, which will help us to understand the dynamics of the process. The graphs help us to study the pattern, the behavior of the process, okay, and brings interesting features with regards to the behavior of the process. Now, in our past class, we've looked at what discrete random variables are, what continuous random variables are. We look at the mass, the probability mass function, and the properties. We also look at the probability density function and the properties. We looked at the cumulative density function as well as the cumulative distribution for the discrete random variable. Today, we want to look at special distributions, okay? And then we are beginning with, we're going to look at a number of discrete distributions. And then when we are done, we'll look at continuous distributions and then what we also use them for, okay? Good. Now moving on. Okay. You toss a coin, there are two possibilities. Either you observe a head or what? A tail. Is that also? So it's either you observe success or a failure. Are we clear on that? Very good. And the probability of the success is equal to 1 minus the probability of what? A failure. Is that also? Are you with me? So we say that given that the probability of the success is P, then you're going to have two possibilities for the PMA. It's going to be P when X is true or 1, and then 1 minus P, that's the probability of failure, right? When X is what? 7. Are you with me? Are you with me? So your response are not encouraged. Are you with me? The expectation.
Yes, sir.
Okay. I'm sure you are still not getting the sound clearly. Okay, it was a live class. That is why there is much feedback in it. But basically, when we talk about a Bernoulli trial, we are talking about an experiment which has two possible outcomes. So for example, the toss of the coin we are seeing here, okay? Once we toss the coin, then there are two possibilities. Either we have a tail or a head, okay? Or in another experiment, we could have a yes and no scenario, or even a success and a failure scenario. So any kind of experiment, random experiment, which will always generate two possible outcomes, is a Bernoulli trial, okay? Now, because there are two possible outcomes, the probability of observing a success, a head, will be what? P. Will be P, and then the probability of observing the tail will be what? 1 minus what? 1 minus P. So we define the PMF as what? That's the probability density function as P when X is a success. X equals to 1 is a success, okay? And then 1 minus P which is also Q, right, is when X is a failure. That is X equals to what? 0. And the expectation of the process is simply the probability of observing a success, whilst the probability of a failure is the probability of observing the success times the probability of a failure. Okay. Now, so let me move on. Okay, then the next thing we want to look at is the binomial process. Okay, for the binomial process is a repeated Bernoulli experiment. So if you toss a coin 3 times, okay, if you toss a coin 3 times, then you have repeated experiment. So this time your n is equals to what? Is equals to 3. Okay, so you could be asked that, for example, if you toss a coin 3 times, what is the probability of observing 2 of them being ahead? Okay, ahead. Or we could also ask you, if assuming we work 5 days, okay, or a machine works for 5 days, what is the probability that with a given probability of success on each day, okay, which is constant, what's the probability that the machine is going to break down maybe 2 out of the 5 days? Okay, so the key characteristics of a binomial process is 1, there should be a number of trials. Okay, there should be a number of trials, or like it's written here, it says the context is